Building effective agents. This was an article written by Anthropic just under 2 months ago, and it goes over 5 agentic patterns that I think that you should know. And I'm going to go over code examples of each of them. Now, I'm not going to go over the whole article here, just the important parts about the agentic patterns. Over the past year, they worked with dozens of teams building LLMs across different industries. Consistently, the most successful implementations weren't using complex frameworks or specialized libraries. Instead, they were building with simple composable patterns. When and how to use frameworks. There are many frameworks that make agentic systems easier to implement, including LangGraph from LangChain, Amazon's Bedrock AI Agent Framework, okay, and then Rivet and Vellum for a more GUI-based no-code platform. And I haven't used those. I'm sure they're good. I prefer N8N. But then they say these frameworks make it easy to get started by simplifying standard low-level tasks like calling LLMs, defining and parsing tools, and chaining calls together. I agree. However, they can often create extra layers of abstraction that can obscure the underlying prompts and responses, making them harder to debug. I somewhat agree with that because I don't really find myself debugging the framework. I will debug Python code as an engineer, but actually debugging the framework behind it. Now, I have when they talk about LangChain and all the version documents they've had to update and how much that is broken, I'm so happy that Crew AI has officially gotten away from LangChain. Nothing against them. Well, I have some personal vendetta against LangChain, just how difficult they've been to upkeep. But I don't really debug the framework that much itself. So then they go on to say that we suggest that developers start by using LLM APIs directly, which I do agree with because if you use the LLM APIs directly, such as using the completions for OpenAI's API, then you just have a basic understanding of how the calls work. Many patterns can be implemented in just a few lines of code. That can be true. If you do use a framework, ensure you understand the underlying code. See, a lot of times people are just saying, just use a framework. We have AI. We can give documentation. It can go through maybe some of the libraries within that framework or some of the code within the framework to understand what's going on if there is an issue, which it certainly can. But this is like something with engineering is if you're going to use a framework, it is good to know how or what the framework is doing under the hood so you have a better understanding. If something does go wrong, you kind of can figure out or understand why it went wrong and then make the fix. Okay, so moving on to the building block right before we get to our first agentic pattern and go over the code for that. So they say that the first building block is the augmented LLM. This is the basic building block of agentic systems and an LLM enhanced with augmentation, such as retrieval, tools, and memory. Tools are just Python functions that allow you to connect to external APIs through the API call or through the LLM, and then retrieval getting like some sort of search query to get some information somehow. These are going to help you with your agentic systems. Now, our current models can actively use these capabilities, generating their own search queries, selecting appropriate tools, and determining what information to retain. That is very true. So we recommend focusing on two key aspects of the implementation. This is tailoring these capabilities to your specific use case and ensuring they provide an easy, well-documented interface for your LLM. That first part right there, tailoring these capabilities to your specific use case. I mean, I think that if you look at the NVIDIA keynote earlier in January, they created, the basic, they had like a researcher agent, right? And what they said was that you have this built researcher agent, and then whenever you want to give it to a company, you copy that, essentially you take in a copy of that, giving it to that company, then you give that company's data, so company A's data, into that agent. So the agent now ingests their data. Now it has domain specific knowledge for company A, but you still have the building block of that original research agent. And that's kind of what they're saying here is like you can build an agent, but for when you go to sell it or when it's being used by somebody else, you will need to have it tailored for that specific use case. And that's okay. You're not rebuilding the agent every time. I think that's just an important thing to understand. So now we're going to get into the first workflow, prompt chaining. Well, what's prompt chaining? Prompt chaining decomposes a task into a sequence of steps where each LLM call processes the output of the previous one. That's like one of the main things there. You can add programmatic checks on any of the steps to ensure that's still on track. So right here, we're starting here. We're giving something to the LLM call, like a prompt. It's going to then get the output. We're going to send that off to the second LLM call, the output of this It's going to be passed into the second one. The output of that will be passed into the third call, etc., until you're done. However many prompts that you're going to use for this prompt chain. Some examples of when to use this: generating marketing copy, then translating into a different language, writing an outline, checking that the outline meets certain criteria, and then writing that document based on the outline. So let's look at a code example. And all this code will be available for you to use. It'll be in my main GitHub AI repository. That'll be in the description. This will be under the 5 agentic prompt examples. So the first one, prompt chaining. So here we go. I have a prompt chain workflow function, right? So I'm not using any frameworks here, right? These are agentic patterns. So it takes in an input query and a prompt chain, which is a list of prompts. So a list of string is just a list of prompts. Okay, so we basically iterate over the list of prompts. Though we call the LLM call right here is run LLM. So we have an LLM call based on that prompt each time. So let me just start right here. I have 3 different prompts right here. So this variable prompt chain, this has 3 different prompts. So it's going to iterate over each one, and the input is going to be the response. So initially, the response, the input query is AI agentic frameworks are the future, or is it? But then, whatever the response of that is, that's going to be passed back in. So the output of the first response can get passed back into this for the next call, and that's going to happen, and it's going to keep doing that until we are done with the prompt chain. And then finally, we basically just take that final answer and we return that. But let's go through this example. So I'm just going to go ahead and run this. So I'm going to say Python prompt chaining. Okay, so here we're starting at step 1 right here. So then it's going to call run LLM. So the first prompt is generate a sample speech, create a TED Talk of it on the topic of the future of AI agents. But the first question is AI agent frameworks are the future, or is it? So the input query right here is that, like, that's the first response, right? That's considered the first response. So I'm asking a question and it goes through the first prompt. It's going to iterate through each of those prompts like I mentioned. So here's step 1. It kind of goes through a TED Talk, through the TED Talk, like the steps of it. Now we're at step 2. So in here, step 2, we're passing in that output as the response now with the next prompt, which is given a speech, only talk about the action items for the audience to take away. So it's saying here are the action items for the audience to take away, from the speech. It gives 4 action items. Then step 3, so now we're in step 3, is taking the action items, pass that in as in the response, and then in the third prompt, given the speech, translate it into Dutch. So now it is doing that. So it took this output, which you can see there's 4 action items, it converted that into Dutch. Okay, and that is prompt chaining. The next flow that they want to talk about is routing. So routing classifies the input and directs it as a specialized follow-up task. This workflow allows for separation of concerns and building more specialized prompts. Without this workflow, optimizing for one kind of input can hurt performance on the other inputs. So what it's saying is, when you use this workflow, routing works well for complex tasks where there are distinct categories that are better handled separately, and where classification can be handled accurately either by the LLM or some other model, right? So saying examples, I'm going to go through the code again so that kind of makes a little more sense, because right now, the way I'm explaining it, it doesn't make the most sense. So examples where routing is useful is directing different types of customer service queries into different downstream processes, prompts, and tools. Routing easy, common questions to smaller models, and then hard, unusual questions to more capable models like Claude 3.5 Sonnet to optimize cost and speed. Okay, so let's go through a code example of this. Now here what I have is I have a router workflow. The prompt is, given a user prompt query, select the best option out of the following routes. Answer only in JSON format. Okay, so let's come down here to what I'm doing. So for each prompt in the prompt list, that router workflow, I'm giving the prompt, and I want to choose the best model for each of those prompts. So that's what it's saying here. For a prompt that I give it different routes to branch off from. So let's look at this again. So there's an LLM call router, and by the way, Crew AI does this with they have a router specific decorator within their flow for this, that I will have another example coming later this week. But so the LLM call router, it's going to decide which of those models based on what they're better at, that I tell it that they're good at, it's going to choose one of those for to get the output, right? So I have this first prompt here, which is to produce Python snippet to check if a number is prime or not. It's going to choose based on O1 mini, 4.0, and 4.0 mini, and also like based on the description I had for each of those. So here, you can see this one is this best model for choice for code generating tasks. So probably, and it should choose O1 mini for this Python snippet to check if the number is prime or not. That's what it should choose. Okay, and that's what's happening. That's what's happening here. This whole router workflow is taking an input, all of the routes that are possible, and I'm asking it to select the best option out of those routes. Okay, so the selected route, this is just this is like an LLM call to kind of get the best route. I'm going to print the selected route with the reason. It's going to give me the reason, and then I'm going to run that LLM call based on that model. Okay, so let's go ahead and run this, and we'll see which ones it uses, and then like make sure that it makes sense as well. Okay, so let's go ahead and let me lift this up. Let's go ahead and run this. Task 1, produce Python snippet, check for the numbers prime or not. Selected route, O1 mini, and that makes sense. That's right here. All right, let me come back up. Yeah, the best model choice for code generating task. Okay, great. We know that was good. Okay, so task 2 is to plan and provide a short itinerary for a travel for a 2-week vacation in Europe. It selected 4.0 mini. So look, if we look at 4.0 mini, that is best model for reasoning, planning, and multi-step tasks. Okay, so that makes sense that it would choose that, and that's what I would prefer it to choose, right? So then the task 3 is to write a short story about a dragon and a knight. It selected GPT 4.0. So if we look at this one, GPT 4.0, I'm saying that's the best model choice for storytelling, role playing, and fantasy tasks. I'm not saying that this model literally is the best for these tasks, but I'm showing you that in these model routes, this is how it can choose with this type of pattern which one is best, because I'm telling it which model I would like it to use, but it's going to decide based off these descriptions which one it should use. Okay, so then it's using 4.0, and then it's giving me the reason, and then I have the response right here. Okay, cool. So again, if we just go over that really quick, just so that made sense. We have a call router. I'm letting it decide based on parameters which call it should make so that it can be optimized the most. Okay, let's go ahead and move on to the next one. The next one is called parallelization. That is a tongue twister. I have a little hard time saying that sometimes. But this is saying LLMs can sometimes work simultaneously on a task and have their outputs aggregated programmatically. So there's sectioning, which you can break a task into independent subtasks, run in parallel, and there's voting, running the same task multiple times to get diverse output. So let's think about this. First off, async, we have async, and we have asynchronous. So I'm sorry, we have sync and asynchronous. Sync means that we're going to sequentially solve problems. So let's say each problem, we have 5 problems, each of them take 2 minutes to solve. It's 2, 2, 2, 2, 2. So that's 10 minutes that it takes. But now if we run things in async, which is parallelization, which is what this is talking about, is if we had the same 5 problems, they each ran 2 minutes, but it was asynchronous, it's only going to take a total of 2 minutes because they're going to all run at the same time instead of one after another. So when to use this workflow, when the divided subtask can be parallelized for speed. I told you, that's a tough word to say. Or when multiple perspectives or attempts are needed for higher confidence results. Okay, so let's go ahead and go through an example of this in the code. Okay, so here I have a function called parallel workflow, except the difference is that it uses async for asynchronous. So now this function is asynchronous, and I pass in a prompt, a list of proposed models that I can use, and then the aggregator model at the end, which I'll show you. So we're going to asynchronously call the function for each prompt. So we're going to run parallel for each model the same prompt. And when we come in here, if you didn't know that there is an async OpenAI call, which again, we have to have some certain things whenever you do this. For instance, we have to have the await keyword in front of this call because this is asynchronous. But other than that, this is a standard call to OpenAI. It's just now it's asynchronous because we want parallelization instead of sequentially one after the other. I have all of these tasks that are running asynchronously. And then here we're going to use a library called async.io, which you can see up here. We just import async.io. It's basically going to take all those tasks and run them concurrent. It says when it runs them concurrently, it means it's running them together all at the same time. Then we're going to aggregate those responses using an aggregator model, which means that we want to run a single call. Now, once those are all those tasks are done running, then we're going to have a single call with all of those responses. And then we are going to put them together and then kind of get the best possible output from all of those responses, because all those responses, you can see we have an O1 mini, O1 preview. I could just as easily add GPT-4o, GPT-4 mini, other models. It doesn't matter. It doesn't have to be OpenAI. But we could have four, like if I had right here, I have two models. So I'm gonna get two different outputs, each output from these. They're gonna be running concurrently together, asynchronously. We're gonna grab both of them, put them into the aggregator model for the final output. So right here, the final output, putting both those responses together, and then this model is going to kind of get the best possible output from both of those responses. And I'm using the O1 mini for that. Okay. Now, with that said, let's go ahead and run this. And this is just the run right here. Again, you have to use this await keyword if you want to run this asynchronously. Okay, I'm not going to go into what exactly that does right now or why. Just trust me. Okay, so let's go ahead and run this Python parallelization. And you see that took like no time at all. It printed this out almost immediately. So this is intermediate response one, that is spelled incorrectly. That is okay. But so it got this response, and then the second one, because there's two models, so we got two responses, and then the solution. So this is the final answer from that one. So then the problem is Jenna and mother picked some apples from their apple farm, blah, blah, blah. Here is the proposed solution because it took both solutions and then aggregated them together. And I had one more regular synchronous OpenAI call, and then it kind of combined, looked at both of them, and then got the best possible response it could just from those two. Okay, and that's if we come back here, this was the voting, where an example they have here, which I think is a really good example, is reviewing a piece of code for vulnerabilities, where several different prompts review and flag the code if they find a problem. That is a really good example of this and kind of what we just did. So and then you can evaluate whether a given piece of content is inappropriate, or multiple prompts evaluating different aspects or requiring different vote thresholds to balance false positives and negatives. Okay, this is a really good agentic pattern. I really like this one. Pretty cool. And this is also one that I think really helps you get a great response or better output. Is this an orchestrator worker? So in this workflow, a central LLM dynamically breaks down the task, delegates them to worker LLMs, and then synthesizes their results, makes it better. Okay, so you can see here we have a prompt coming in with orchestrator. It over here delegates them to worker LLM, so we have multiple LLM calls, and then brings them back together to get the best possible output. So when to use this workflow is well suited for complex tasks where you can't predict the subtask needed. Encoding, for example, the number of files that need to be changed and the nature of the change in each file likely depends on the task. Okay, example where this is useful: coding products that make complex changes to multiple files each time. Search tasks that involve gathering and analyzing information from multiple sources for possible relevant information. Let's go over an example of that now. Okay, so this looks a little different because this is a little bit more thought out beforehand. So I have an orchestrator prompt that's going to analyze the task that's given and break it down to 2 to 3 distinct approaches with the task and provide an analysis for those. So it's supposed to also provide 2 to 3 approaches to tackle the task with a certain description for each of those. And then for the worker prompt, so it's going to generate content based on the task, the style, and the guidelines that it will be given. Okay, so The actual task is to write a product description for a new eco-friendly water bottle. The target audience is environmentally conscious millennials, and key product features are plastic-free, insulated, and lifetime warranty. Okay, so right here, this is just using Pydantic to worry about type safety. Again, I have async, right? We saw whenever you see something like this right here, LLM call 1, 2, and 3, like on a graph, and it looks like this, that's more than likely asynchronous, meaning that they're going to be concurrently running together. Okay, so the orchestrator response, okay, this is going to take, this is one LLM call, and then we are going to parse the orchestrator response. So we're going to take the analysis and the task. So now the orchestrator output is, this is just going to give us the orchestrator is going to say, here's the analysis and here are the tasks that we need to solve. And now the worker model is, we're going to have multiple workers depending on what those tasks are. So you see this length of task is going to just, we're going to make multiple of these. Basically, this big long line of code that I don't really like, that I will probably make it better, easier to read, but this await async io.gather, it's basically run LLM parallel. So we're going to be having a lot of async open AI calls here, depending on how many tasks there are. And it's going to come in here for each model and then run those. Okay. So it's going to get the responses from those worker model. I think it's going to be best if we just run this and then go back over some of this. So let's go ahead and run this at Python orchestrator workers.py. Okay, so here, right here, orchestrator output right here. So there, it's taking that LLM response from the orchestrator response. We're going to gather the analysis and the task from there. And now it's just printing them out. So the analysis of the task is centered around crafting a captivating and informative product description for a water bottle. Now it gave 3 different tasks, one with the type of formal, conversational, and hybrid, and a description of each of those tasks. Okay, so what's happening here is the workers. So for the formal one, this worker is coming back with a response. For the conversational, this worker is coming back with one. And for the hybrid, this worker is coming back with a response. And then what we would do is we would take all those, and then we can do something with that output. We can synthesize all these outputs as well, and then combine them into one if we would like. Okay, but so this is another way of basically having a task, delegating the task by creating new tasks, and analysis by getting analysis of it, creating a task, having these workers, concurrently running for different ways that you would like to have the result of that task, right? So here we had a hybrid, a formal, and a conversational, right? Those were the different ways that we wanted. That was kind of like the style. So that was the task type for that. And so it took right here, formal style, write technically and precisely. The conversational was write in a friendly and engaging way. And the hybrid was tell a story that includes technical details, right? So these were the different styles or ways that we wanted the workers to write. So we took the tasks and we had the different workers running concurrently to write and give us responses based on those. Okay, so this is how the orchestrator workers works. In this last one that I think you have seen and is actually very helpful for many different things is the evaluator optimizer. So in this one LLM call generates a response while another provides evaluation and feedback in a loop. So this is really a simple feedback loop that, is within AI. You don't need a human in the loop here. Like you don't need to tell it, right? This is just AI generated. So when to use this workflow is particularly effective when we have clear evaluation criteria and when you need to maybe iteratively refine based on those measurable values. Okay, so when is this useful? Literary translation, where there are nuances that the translator LLM might not capture initially, but an evaluator LLM can provide useful critiques for. You can also have complex search tasks that require multiple rounds of searching and analysis, right, to gather comprehensive information, which is great, right? Because a lot of times when I'm getting like Google News or something, I don't always get all the data that I would like to have. So something like this would be very useful. Okay, so let's go through a code example of this. What you may not know is that when I initially started YouTube, back right after COVID happened, I did computer science for like within like the first 3.5 years. I took a break for almost 2 years, but also before those 2 years, 2020 and 2021, I just did straight computer science topics based on data structures and algorithms. If you were to really go back in my videos, like starting from the oldest, you're going to see data structures a lot. I went through like a whole book that I had in my master's program, and I went through all that. And a stack is like the simplest data structure that you should know. Okay, and um, get min, yeah, but push and pop are the two here that you really should know how a stack works. Okay, but either way, we have a task here to implement a stack. The generator prompt says your goal is to complete the task based on the user input. If there are feedback from your previous generations, you should reflect on them to improve your solution. Okay. So what we're doing here is I have a generate function. This is just, the full prompt is to basically from here with given the context and everything, create the stack. Okay. Then we have an evaluator prompt. So now this is a generate function. Now we have an evaluate function. So based on this evaluator prompt and the generated content, we basically want to make sure that this passes, right? So we either give it pass, needs improvements, or fails. And this is just a single LLM call as well, okay? So now if we have this, now what we have is this loop workflow where we're given a task, the evaluator prompt and the generator prompt. We're going to keep generating and evaluating until the evaluator passes the last generator prompt. Okay, so what we have here is basically we have to have a way to store the previous responses so that we know what to improve on. We're like, you did this already, improve on this. Okay, but here's the initial response. We're going to generate the initial response, append that to the memory. So now we are in just a while true. If you want a continuously everlasting loop until you break out of it or something just completely breaks, while true. So now what this is doing, given with this evaluate function, we're given the task, the evaluator prompt, and the initial response. So this will be like the initial code it creates. So the determining condition, if it passes, just return. Okay. If it doesn't, meaning you add the current response and feedback to context and generate a new response. So if it doesn't pass, then here, right? This is what we basically want to regenerate and add that to memory again. And then we're going to evaluate it once more. So we basically are in here until we return, and that brings us outside of the loop. Okay, so let's go ahead and run this now. So the loop, Python evaluate optimizer. So I'm going to bring this up, and all this is going to do, it's going to probably create the code. I mean, this is a very simple piece of code. So to implement a stack, the generation start, implement a stack with push, pop, and get min operations all in one time. Okay, so it's going to use two stacks. Okay, yeah, whatever. It's going to, here's the Python code for min stack. It says this implementation efficiently manages required operations. The evaluation start. So the status is needs improvement. I'm actually kind of surprised about that. I thought it would maybe just fail or pass the first time. So the feedback and the evaluation is code correctness. So this is it giving feedback. All right. And then it's going to generate it again. Okay. So the generation start, the output thoughts, the task requires implementing a stack with efficient, whatever. So it's going to try and improve based on that. And then now it's going to evaluate it again. And now the status is passed because it's passed. Here's the feedback on why. And then it returned, if the evaluation is passed, it returned. We come out of the loop and we're done. Okay, so I'm happy that it actually didn't fail, that needed improvement. I'm happy you did that once so that you could see that this is self-improving with the evaluator response. This is very good. This is also a pattern I think you should really understand. Okay, I mean, that's building effective agents. And we didn't even go over this whole article, right? This is a big article. I think it's an important article, especially understanding these five agentic patterns. Okay, I'm going to have the GitHub again in the description. I'm going to have this paper in the description. And also, if you want to create AI agents, I have a community in the description. I'm going to help you solve your problems and make your goals. Come join. There's a free trial right now. I would love to see you and join